Hello and welcome to the fourth and final video of the FP1 chapter Proof and the final video for the entire FP1 module. Start a question on the screen to remind us about matrices. Given that A is this 2x2 matrix, find A cubed. To do this we multiply A by itself 3 times, and usually the order of matrices is very important, but because this is the same matrix 3 times, obviously it doesn't make any difference. Now I'm going to do 2 of these first, and once they're in their place it doesn't matter which 2 I choose. So here we've got 9 minus 2, give us a 7, 6 minus 0, minus 3 plus 0, and minus 2 plus 0. And then we've still got the third matrix to give us a final matrix: 21 minus 6, 15, 14 plus 0, minus 9 plus 2, and finally minus 6 plus 0. In this video, we are applying proof by induction to prove results involving powers of matrices, specifically powers of matrices like this, because if it's the same matrix with a power on it, it does not matter what the order is. That's useful in these results. Going straight into the examples, prove by induction that for all positive integers n, this matrix to the power of n is equal to this matrix. This is a little bit more straightforward than the previous 2 videos. We just apply proof by induction as we know. So when n is equal to 1, on the left hand side we get 1 minus 1, 0, 2 to the 1, which is obviously just 1 minus 1, 0, 2. On the right hand side we get 1, 0, 1 minus 2 to the 1, 2 to the 1, which is 1, 1 minus 2 is minus 1, 0 and 2 to the 1 is a 2, which is the same thing. Therefore this statement is true for n is equal to 1. Then we assume it's true for n is equal to k, 1 minus 1, 0, 2 to the k is equal to 1, 1 minus 2 to the k, 0 and 2 to the k. Then we take it for n is equal to k plus 1. And hopefully we can show this result here where n equals k plus 1. To do that, we're going to split this matrix into 2 parts. The first part, we're going to have this to the power of k, and just using your normal index rules, that means I have to multiply it by itself 1 time here. And this is where the power thing comes into play, because it doesn't matter if this is on the left or on the right, because it's the same matrix multiplied by itself many times. So either way you put it, you can then replace the matrix power k with our assumed result, and then apply your normal matrix multiplication. And hopefully you can manipulate it to look like the result you need. So here we have 1, all of this times 0, so that's just a 1, minus 1, and then 2 times all of this thing. So we've got minus 1 plus 2 lots of 1 minus 2 to the k. I'll tidy that up in a moment. On the bottom, 0 plus 0 gives us the 0 we need, and then we've got 0 plus 2 times 2 to the k. 2 times 2 to the k. Now this one here is fairly straightforward. We bring the 2 into the index here, we get 2 to the k plus 1, which is what we want. Up here, I'm just going to expand this out a little bit with another line of working on the side here. 1, 0, 2 to the k plus 1 there. And then here we've got minus 1. Expanding that bracket gives us plus 2 minus 2 times 2 to the k. Just to make it really super clear for the examiner, here of course we've got plus 1, and here this 2 can come into the index as we did down here to make this 2k plus 1, and that matches what we want because of the minus in the middle. So we've got our 1, our 0 there still. Here we've got 1 minus 2 to the k plus 1, and here we've got 2 to the k plus 1. And when n equals k plus 1, this matches. So this is true for n equals k plus 1 if it's true for the assumption that we used when n was equal to k. And as usual, together with this basis statement, we can now say, therefore, it must be true for all natural numbers. I keep saying natural numbers on these videos. In the textbook, they use positive integers, this symbol, but that's the same thing, natural numbers and positive integers. Final example of the module, prove by induction that for all positive integers n, this to the power of n is equal to this. Same idea, nothing funny going on here. Basis step, when n is equal to 1, left-hand side, we get minus 2, minus 1, 9, 4 to the 1 is obviously equal to minus 2, 9, minus 1, 4. Right-hand side, we get minus 3 times 1 plus 1, and minus 1 down there, 9 times 1 up here, and a 3 times 1 plus 1 over here, which gives us minus 3 plus 1 is minus 2, 9 times 1 is 9, minus 1, and 3 plus 1 is a 4. They match, therefore this is true for n is equal to 1. Our assumption, we are assuming it's true for n is equal to k, minus 2, 9, minus 1, and 4 to the k. We're assuming is equal to minus 3k plus a 1, 9 times k, minus k, and 3k plus a 1 down here. Then, same as the previous example, we do this matrix to the power of k plus 1 and split the index, so we have minus 2, 9, minus 1, 4 to the power of k, times by minus 2, 9, minus 1, 4. Replace that first matrix with our assumption, minus 3k plus 1, 9k, minus k, and 3k plus 1. Multiply it by this matrix here, and simplify. So we have minus 2 lots of this, so that gives us 6k minus 2, 9k times minus 1, so that's minus 9k. Second element, this times 9, plus this times 4, gives us minus 27k plus a 9, plus 36k. Then we have 2k minus 3k minus 1. And finally, we get minus 9k plus 12k plus 4. Now our job is to get this to look like this, where n is equal to k plus 1. And this does take a little bit of manipulation. Let's tidy this up first. We've got a minus 3k minus 2 here. Over here we've got a 9k plus 9, minus k minus 1, and 3k plus 4. So I think this one here is quite obvious. We just factorize out the 9. Same here, factorize out the minus 1. This one is okay. We can split the 4 here into a plus 3 plus 1. Then factorize out the 3, and we still have the plus 1 on the end. This one is a little bit more awkward, but it's the same idea as this one. We are going to change the minus 2 into a minus 3 plus 1, which obviously is the same, and that lets us factorize out the minus 3 and leaves a plus 1. So I'll just write that out really clearly here. So we've got minus 3k minus 3 plus 1. Factorize out here k plus 1 in the bracket. Factorizing the minus k plus 1 in the bracket. And then 3k plus 3 plus 1. I don't think I can be any clearer than that, so let's put this in its final form. And that matches what we've got here. K plus 1 in here, k plus 1 here, k plus 1 for this, and here k plus 1. Therefore, this is true for n equals k plus 1 if it's true for our assumption when n is equal to k, because as usual we did use that in this process, and that together with our basis means we can write it is true for all n in the natural number set. And there you go. You can now practice for matrices with proof by induction, exercise 8D, for all of the proof by induction, chapter 8 review exercise, for the second half of the textbook, review exercise 2, and for the entire module, the exam practice if you've got access to the textbook. And maybe I'll see you in FP2.